lunch and academic year. We have a lot of new faces, so let me start by mentioning the new postdocs that arrived as of the last week or so. We have new postdocs at the ITC, and please raise your hand when I mention your name. The first is Sonak Bose. Is he here? Oh, here he is. He's coming here from Durham. Well, the weather is probably worse, right?
Well, I was greeted with rain as the first thing in Massachusetts yesterday as well. So
but our accent is not as good.
Well, I won't say anything about that.
We have also Rahul Kanan from MIT, not far away. Well, I guess there is a lot of traffic. He's an Einstein fellow. We also have Antonia Oklopic over there. And Anna, she came from Caltech. And Anna Rosen from UCSC. Where is Anna?
I think she's giving a talk today.
Oh, she's giving a talk. And speaking about another postdoc that joined us. Now you are not a member of the ITC, you are at the CFA, and you are an Einstein fellow.
That's right.
Exactly. And we have two more postdocs that are related to the Data Science Initiative. That's a new initiative on big data at Harvard. One of them is graduating next month. Her name is Michelle Tampaka, and she's not here from Carnegie Mellon. She will start on November 23rd. And Laurie Shaw came here from the University of Cambridge. Is Laurie here?
He'll be here.
Oh, okay. He will arrive in a moment. Then we have a sabbatical visitor to the ITC, Michael Joyce, over there, who has an Irish accent, but he lives in Paris, actually. And he works on dynamics and large-scale structure. He's a professor of physics at the University of Pierre and Marie Curie in Paris. And then I would like to mention 6 new postdocs that arrived to the Black Hole Initiative. So as many of you know, this is the only center in the world that focuses on the study of black holes. And it brings together people from different disciplines, astronomy, physics, mathematics, and philosophy. And so let me mention them in alphabetical order. First, the philosophy postdoc is Faraz Azhar. He just arrived last week. Oh, he's there. Great to see you. I haven't met him actually. Did you find an apartment?
I actually told you today.
Okay, so I know that you put a bid, but I didn't know if you got it. Okay. So Faraz is coming to us from the other Cambridge, the original, the actual original. And he finished his PhD in philosophy. Then we have Mislav Balokovic, who is currently in Poland. I just corresponded with him by email. He's attending a conference, and he came from Caltech. He works on the Event Horizon Telescope, and he's also married to Antonia. So we managed to solve a 2-body problem to our advantage. Also in physics, we have Laura Donay. I don't know if she's, oh, here she is. She works on string theory and related physics. And we have also Tsinyu Chen, who works on gravitational wave astrophysics. She is attending a group meeting of the LIGO collaboration. And by the way, one of the things that happened over the summer, for those of you that were under a rock or in some beach, is that LIGO detected some additional events. Not 1, not 2, I think order 3, but they haven't publicized it yet. But one of them is particularly interesting based on rumors. And these rumors were leaked out to the press. And when I sent a message about them, I got replies from some people that know, that said, no comment. Now, I actually didn't ask them for any comment. And the fact that they said no comment means that they do not deny it. And the reports were about a potential event that has an electromagnetic counterpart. And potentially two neutron stars crashing, coming together and producing an electromagnetic counterpart that could result, for example, from a little bit of neutron matter that gets thrown out of the system. So we all look forward to their public announcement, which we hope will be during the month of September, perhaps in a couple of weeks or so. And of course, we'll feature it in the ITC lunch when it's announced officially. We also have a Black Hole Initiative postdoc in mathematics. His name is Jordan Keller. Oh, here. He came to us from Columbia University. And finally, an astrophysicist, Maciek Wilgas. Is he here? No. And so, as you can tell, all six work in different disciplines, and we hope that they will speak a common language by the end of their stay and collaborate. English. The other thing I wanted to mention is that we will have a group photo at the end of this lunch. So everyone should step out at around 1:30. And finally, most importantly, the ITC lunch, as of this year, is sponsored by a generous donation from the ITC senior member, Dr. Eric Quito. Is Eric here? Over there. And we are really grateful for Eric. As you know, Eric sponsored also a prize that we award once a year to the best PhD in theoretical astrophysics at Harvard. And so now this is the second donation that he provides to the ITC, and we are grateful for that. Okay, so we just had a wonderful talk by Sukanya Chakrabarti, who is visiting us from the Rochester Institute of Technology, and she will speak in a few minutes about something else. We'll start with Pierre Christian, that will talk about testing the black hole no-hair theorem with electromagnetic fields. Then we'll hear from Sukanya, who will talk about the subject, is the vast polar structure of dwarf galaxies a serious problem to Lambda CDM? Then we'll hear from Wystan Benbow at the CFA about the recent highlights from the VERITAS AGN observation program. And finally, we'll hear from Razieh Emami from Hong Kong, who will talk about probing the scale dependence of non-Gaussianity through the CMB Spectral Distortion. Pierre.
All right, thank you, Avi. It's my pleasure to start the semester. And today I'm going to talk about this project, which is testing the black hole no-hair theorem using electromagnetic fields. So the idea itself, the concept is actually relatively simple, but since there's a wide variety of audience here, I'm going to go through it somewhat pedagogically. So first, what is the black hole no-hair theorem? So people have probably heard of the idea that black holes have no hair. So what that means is that black hole metrics, they depend only on three numbers. They only depend on the mass, the spin or the angular momentum, and the electromagnetic charge. In other words, the metric has to be given by either the Kerr metric or Reisner-Nostrom solution. So black holes actually have three hairs. It's not no hair. So this is proven in the mid-70s under the following assumptions: that first, general relativity is the correct gravitational theory, that there is no closed time-like loop. What this means is just there is no time travel into the past, and that nature abhors naked singularities. So if, suppose, we found in nature a black hole that violates the no-hair theorem, then one of these three consequences is true. It's either that GR is not the complete picture of gravity, or that there are closed time-like loops allowing time travel into the past, or that there are naked singularities. And all of this have significant repercussions to both physics and also philosophy, That is, if 1 is false, then it is a clue towards quantum gravity. If 2 is false, then causality goes out of the window, and there's all sorts of paradoxes. And if naked singularities exist, then determinism breaks down. Now, you ask me amongst these 3 things, like which one I would prefer. I think I'll prefer 1, because 2 is too scary and 3 is too weird. So if a non-hairy black hole is that given by Kerr and Reissner-Nordstrom, then what's a hairy black hole? So there's a wide variety of metrics of black holes. So let's focus on a particle subset of them that is asymptotically flat, stationary axisymmetric spacetime, which the Kerr solution is a part of. So roughly speaking, asymptotically flat means that the curvature goes away far from the black hole. And this makes sense because far away from the black hole, you don't want to feel any gravity. Stationary means it has time translational symmetry, and axisymmetric has rotational symmetry on one axis. If these words is not familiar, we're going to cover them more later. So actually, there is a metric that you can write that is general, that is both stationary and axisymmetric, and is asymptotically flat. This is called the Wald metric, and it's given by this equation here. It's somewhat complicated, but not really actually, because all these parameters nu, b, omega, zeta are just like stuff we do not know. And they're just functions of r and theta. Okay, so this is basically just a general thing. And for example, for the Kerr metric, you put in a particular value for what nu, you put in particular function of nu, b, omega, and zeta. And I'm sorry, this is not the magnetic field. That's just b. So Butterworth and Ipser in 1976 performed an asymptotic expansion upon these metric functions. The details are not important, but things like this come out. For example, you have this nu. You perform an asymptotic expansion, you get something that looks like this. Okay, so let's revisit the no-hair theorem. Look at this expansion. This is actually an expansion over 1 over r, right? And in the beginning of every single power of 1 over r, there's a coefficient. The no-hair theorem basically says that all of these coefficients will have to be a function of either q, m, or j, one of these 3 things. That's essentially what the no-hair theorem is saying. So if we found a black hole in nature, and then we measure, for example, the coefficient behind this, like this one, and found it that it's not a function of q, m, or j, that means that black hole has violated the no-hair theorem. So this is actually just a multiple expansion. And there's so many coefficients. There's like an infinite amount of expansions. So let's not deal with that. Let's just deal with the easiest correction, which is the quadruple correction. So a black hole that obeys the no-hair theorem will always have a quadruple moment that is given by this, negative j squared over m. This is the quadruple moment of a Kerr metric. So that's the kind of complicated point of view that I have to give because there are some people here who want to see that stuff. But it's actually easier just to think of it this way. There's a non-complicated point of view. You have a black hole, looks really nice. It has a quadruple of negative j squared over m. That's the Kerr black hole. And we are interested in a black hole that looks like this. And it looks kind of wonky. And it has a quadruple moment that is not just j squared over m, but it could have a third parameter that is not either mj or q. And this black hole with this kind of quadruple is something that violates the no-hair theorem. So how do we add this extra quadruple? It's actually very easy. So your metric is g mu nu, and you just have g mu nu of Kerr, and you add a correction that has an extra quadruple. The correction that people usually use is that given by the Harter-Torr metric. So this is the metric that is usually used to study neutron stars. And as you know, neutron stars have arbitrary quadruple. So this is just a metric that's basically a Kerr plus something that has a quadruple. And in front of this metric, we put this epsilon, which is a small parameter. Okay? This is called the quasi-Kerr metric. And what we are interested in is if we submerge black holes inside the magnetic fields, what will happen? It's easy to figure out what happens in this case. It just does something like this. It's actually quite easy to calculate. In fact, the hardest part is actually drawing this in PowerPoint. And this one, we do not know how it works. So it's a question mark. And in order to solve this one, you have to solve Maxwell's equation, which is given by this. It's the source-free Maxwell equation plus the Bianchi identities. And you need to solve this in curved spacetime, so it's difficult. However, there is a trick. There's this trick by Wald that says magnetic field inherits the spacetime symmetry. what does this mean? What does this mean? It means like, if space-time doesn't change if I rotate stuff around, then probably the B field doesn't change if I rotate stuff around. It makes sense that it has to be that way. Okay? So what is the symmetries of this metric? So like I said, it's stationary and axisymmetric. So this is a complicated table if you are not familiar with this language, but all you need to know is essentially this column here. There is this concept in relativity called the killing vector, which is basically the direction in which there is a symmetry. So for example, if in this plane, if I move this way, nothing changes, then this is a killing vector. That's all it is. So the killing vector for stationary means time translational symmetry, points in the time-like direction. It points in the time. And space-like, this asymmetric symmetry, it's pointing in the rotational direction. Okay, that's all you need to know. There's an easier way to think about this. Stationary just means you have your black hole. You add some time, you wait. It's still the same black hole. Okay? That's what stationary means. Axisymmetric means you have your black hole and you rotate it around and it's still the same black hole. And each of these symmetries have a vector pointing towards where that's, that's symmetry. So the killing vector, I call this eta, for the stationary time-like symmetry points towards in the time direction. Okay, the time-like direction. This one points in the rotational direction. All right? So, again, magnetic field inherits the space-time symmetry. What that actually means is, if you talk in terms of the vector potential, A, it's basically just saying that A alpha is just a linear combination of those two killing vectors. So it's just some constant multiplied by the vector that points at time plus a constant that points to a vector that points in the phi direction. Okay, that's all it is. Now, instead of working in alpha, I'm going to work in F, the electromagnetic tensor, because F is closer to E and B, at least. Well, that's debatable, but sure. But C1 and C2 you can find basically by imposing boundary conditions. As a refresher, what this F is in flat space-time, F is just, it's an honest-to-God tensor. It's just like this 2x2 matrix that is basically a collection of these E and B fields. Okay, so whenever you see F, this is just like E and B. Okay, so if we calculate this F for that metric, what you get is something that looks like this. This is just a theta phi component. This looks like somewhat complicated, but actually it's not. Schematically, this is just the Kerr magnetic field plus epsilon, the small parameter, multiplied by some quadruple term, some correction. So all of them basically looks just like Kerr plus some quadruple. Is that? All right, so now we have this F. How do we get the B fields from F? Well, the B field is not a covariant quantity, so we have to choose a frame. In this business, we usually choose what's called the Zamo frame, which is the zero angular momentum frame. And it's defined by, you have angular momentum, and you just set it to 0. Okay, that's literally what it says in the tin. One thing to notice that zero angular momentum is not equal to zero angular velocity. If you have frame dragging, then even if you have zero angular momentum, you'll still get dragged around. Now, we take the Zamo frame, which is different from the Zamo frame from Kerr, so we actually have to calculate the Zamo frame for this metric, but I'll spare you the details. You can just project all your F mu nu into the Zamo frame, and then you can read off E and B fields from this. Okay, again, this is what F mu nu in flat space-time looks like, and then you can just pick out E, B, blah, blah, blah. For notational convenience, we split F mu nu into F mu nu Kerr part plus epsilon times F mu nu of the quadruple part. An example of the quadruple part is this. There's some time dilation going on. Here's one component. This is a magnetic field in the R direction. It looks something like that, but let's just plot this to see how important these epsilon terms are. So the first plot here is the magnetic field, the quadruple contribution as a function of radius, and it's normalized over the magnetic field if there is no black hole there. Okay, so it goes higher and higher as you get closer and closer to the horizon. And this solid part is the radial component, this dashed part is the angular component. This one is the same thing, but normalized over the Kerr values. So as you get closer and closer to the horizon, you saturate around at a value of epsilon. Here in this plot, I set epsilon to be 1. So here you can get like a huge amount of correction. However, for real black holes, epsilon could be very small. So the normalization could go very much smaller than that. Another thing that people like to show is the ENM invariance. Like I said, the magnetic fields are not really covariant. So it's actually better to plot these type of covariant quantities. So we'll plot just one of them, F nu, otherwise known as B squared minus E squared. And here's the plot. The dashed line is for spin 0, and sorry, solid line is spin 0, dashed line is spin 0.9. And this is as a function of radius, this is a function of angle. The more interesting one is this function of angle. If you work with multiple expansions a lot, you will notice already this is a quadruple. So basically, the magnetic fields inherit this quadruple structure. I mean, it sort of makes sense. You put in a quadruple, you get a quadruple back. All right, so the conclusion, black holes that violate no-hair theorem, they possess B fields that have this like weird angular structure. And the modified B field could be as high as this epsilon parameter. And this actually modifies the motion of charged particle. For example, the ISCO changes close to the horizon. What about electric fields? So I've been saying about magnetic fields. So magnetic black holes are probably more common. However, spinning black holes are charged at least a little bit. This is known as the wall charge. And then actually, there's a transformation in ENM. You can do that. You can just switch B to E just by using this Hodge dual. So, and it's, so because I've already done all the work for B, actually I get all the work for E automatically. All right, thank you.
Yeah, I just have one recommendation that when you go to a conference abroad and you pass security, never say that you work on killing black holes.
Well, these are technically killing fields.
Thinking about this now in terms of observability. So obviously you don't know what epsilon is.
Right.
It could be very small, but what kind of measurements? Are there any existing measurements or any constraints on it?
No, epsilon is pretty much unconstrained. So, for example, for gravitational waves, the epsilon parameter is actually degenerate with a lot of the other parameters, and you need a lot of inspirals to do it. So it's not feasible, at least for current generation.
Just to follow up to that, what about the image from the Event Horizon Telescope?
Yeah, that would be the first kind of measurements of epsilon. But there's also an importance in, you cannot just measure epsilon for one black hole. You don't measure a black hole and say it has spin 0.5 and say all black holes have spin 0.5. We need a general way to measure many, many epsilons. The same way we need a lot of, like a general way to measure a lot of spins for different black holes.
Any more comments? Let's thank Pierre.
So hi, I'm Sukanya Chakrabarti. I was a postdoc here a while back, so it's great to be back here and see so many familiar faces. I was asked to talk about something totally different from the talk that I gave earlier. So that's what I'll do now. This is work that has been done mainly by my former PhD student, Andy Lipnicki, who looked at the dynamical time evolution of the dwarf galaxies that belong to the so-called vast polar structure. It's been known for some time, in fact since the 70s, that the dwarf galaxies around the Milky Way line up preferentially, kind of in a plane. Okay, so here's the disk of the Milky Way, and these are the classical Milky Way satellites that seem to line up in a planar structure. And it's not obvious that you would expect something like this if you were looking at cosmological simulations that tend to produce more isotropic structure. So we wanted to ask the question if this kind of structure is a serious problem for Lambda CDM. So in a paper that we wrote recently, we've now added here all of the known dwarf galaxies at the time of publication, okay, including the ultra-faint dwarf galaxies, the ones from DES, etc. And the two questions that we're asking is, one, does the structure disagree with simulations, probabilistically that is? And the second question also is, if you were to look at the time evolution of this kind of structure, because you have proper motions for these dwarf galaxies, so you can integrate the orbits backward in time, and you can ask the question, does this kind of structure maintain dynamical coherence? Okay, so this is a very simple calculation to do with, say, orbit integrations, because we have the proper motions from HST observations. And if it were to maintain coherence, then it certainly would be a bigger problem for Lambda CDM than if it were not. So what Andy has done here is he's found the best fit plane for the dwarf galaxies. Okay, this quantity DRMS. It's just the vertical distance that a dwarf galaxy lies from the best fitting plane. And then he normalizes by the median radial distance of the distribution as a whole. Okay, so this is similar to what's been done in prior work. Okay, so what we're doing here now is comparing the, this is the Milky Way distribution. The quantity delta here is the vertical distance of the dwarfs from the plane, normalized by the median radial distance. This is where the Milky Way lies, okay, for the dwarf galaxies of the Milky Way. And this is the PDF that he's built up by choosing 11 satellites from 3 different cosmological simulations, Via Lactea, Aescula, and IHAL, and fitting a plane to that distribution. Okay, and he's repeated that process many times to build up a PDF. So the Milky Way doesn't lie right on smack, in the middle of it, but it's only about 2 sigma, okay, off. All right, so that's the first result. So it is more or less in agreement with simulations. And secondly, you can very easily now look at the orbits of these dwarf galaxies as a function of time. You can just integrate given the HST proper motions, you can integrate the orbits backward in time. Okay, so this is starting from present day, and this is integrating backwards. Okay, and we've split this up into different subsets. Okay, so we've looked at all of the classical dwarfs. If you integrate those backward in time, the structure disperses quite quickly within about a dynamical time. Okay, if you take out the Leo 1 and Leo 2 dwarf galaxies, which some have claimed don't really belong to the vast polar structure, the same is the case. If you only look at the dwarf galaxies that have aligned angular momentum vectors, okay, that's also the case. And finally, obviously, these measurements have errors associated with them, and we came up just experimentally with some constraints on how large of an error you could still have and still trust the orbit integrations using the proper motions. Okay, so what I mean by the trusted proper motions are the ones that, where you can do the orbit integration and still trust these results. And for this case also, for this subset also, the planar structure disperses within a dynamical time. So it's clear, I think, that this is not a dynamically stable structure. And this is just a movie that shows the backward integration. Okay, so you see that the satellites disperse quite quickly. So, so I would say, in answer to this question, that it seems that the structure is not in any real disagreement with Lambda CDM simulations. And secondly, also interestingly, this structure does not appear to be dynamically coherent. Okay, so especially I think for the ones that where the proper motions are have relatively low error SAG, LMC, SMC, Draco, Sextans, Fornax, and the two Leos, we can certainly trust the orbit integrations there. And we also outlined the few for which somewhat better measurements would improve the robustness of this conclusion. So I'll end here, and I'd love to take questions. Thank you.
The fact that the Wystan structure and the result of the fact that small galaxies enter the host galaxy, but filaments or sheets,
Right.
otherwise, why wouldn't you get some round distribution? Or why do you get a preference for a narrow region?
Yeah. So we didn't look at that specifically. I mean, it would be easy to generalize this and look at this, by adding on a tidal field that represents a larger region. But various people have, made the suggestion. Libeskind and others have found that these structures do tend to be aligned with large-scale filaments. Now, in terms of connecting this to the dynamical stability of the structure, that's a sort of separate question. So that says that it hasn't really maintained this kind of planarity for too long.
But it brings the interesting possibility of looking for filaments around the local group.
Right. Yeah. Yeah. So there has been a work that's looked at this. I'm forgetting the name of the first author, but he does find a general kind of correlation between these between the dwarf galaxies in these planes and on larger scales locally. But I'll be able to look that up for you later. I'm blocking the last name.
So, and I'm sure there are really important selection effects.
Of course, yeah,
So
yeah.
when you did the test, the
Yeah.
n-body simulations, did you take that into account?
Yeah, so we didn't, but it's been taken into account before. Actually, maybe I'll just mention this briefly. So it's been taken into account before by people like Pawlowski and others, and Charlie, I guess you're talking about the fact that there is obscuration close to the plane, obviously. So surveys, particularly optical surveys, may have missed some of the dwarf galaxies. So that's one way of resolving it. You tend to find that typically you'd miss maybe 20 to 30%. Infrared surveys have been improving on that, like the Vista variables of the Via Lactea. We've potentially, this has been ongoing work, and I didn't talk about this earlier, but there is a cluster of variable receding stars about here that may or may not be a dwarf galaxy. So, but there are now, I think, the selection effects potentially with these newer infrared surveys are a little bit less.
As you may know, there are many other directions of research that imply that we have polar flows entering our galaxy, and would be one of them, and Cooper discussed it, most people do. But my question is, these other indicators of polar inflow, namely the sub-millimeter arrays detection of such an inflow, namely the Sagittarius streams and other streams showing inflow into our galaxy. And then if you look at Sagittarius A star, it appears to have an accretion disk which is polar inclined to the plane of the galaxy. Do you know if anybody has yet checked to see if all of these inflow planes are in fact the same planes within areas?
Yeah, I don't know off the top of my head.
Thank you.
Okay, well, we need to move on. Let's
Okay, so my name is Wystan Benbow. I'm the director of the VERITAS project, which you can see down here. And I'm giving the colloquium later today, so I was asked to give a talk that was different, and so I decided to focus a little bit on my specialty, which is the AGN research program of VERITAS here, which I can't talk about in very much detail this afternoon. And this is very much my baby in VERITAS. It's what I have devoted most of my energy to scientifically over the past decade or so. And if you look at VERITAS, what is VERITAS? I mean, VERITAS, we study very high energy gamma rays from astrophysical sources, and so our threshold is about 85 GeV, and we do research from about 85 GeV up to 30 TeV. We've been operating now for about a decade, and it's an evolving observatory. You can see that we've moved a telescope, we've replaced our cameras, we've put in control buildings. Things have gotten better and better and better over the years, and so we've done bigger and better things, of course. We take about 1,300 hours a year worth of data, about 1,000 hours in what our best time, our dark time, and we get about 300 hours a year in gray time, where our energy threshold is about twice as high as it would be during dark time. And the key point I'd like to point out, especially to theorists, if you look at our data, the systematic errors are very important in what we do, and the flux measurements, our typical systematic errors are about 20%. And this is because the atmosphere is our calorimeter, and there's just very little control over that. And then most of our photon spectra that we measure, we're statistics limited, and so you typically get power laws out of these photon spectrum, and the systematic errors on those are about 0.1, and you're just not going to do better than that. If you look at the VERITAS source catalog, what you see up here is it plotted in galactic coordinates. The red dots you see up there are AGN. The blue shaded region is the visible sky. As you go down in the sky, our energy threshold spikes, so the visible region is really the blue area, and that's where we want to do our AGN research. And you see that we have about 60 sources from 8 different astrophysical classes. About 65% of these, give or take, are extragalactic, and most of these extragalactic sources, save our good friend M82, are AGN. There it is. So AGN, for those who aren't as familiar with these things as I am, you basically have a unified model over there, and the main thing you want to focus on is that there's a very large black hole at the center of these things, and about 10% of these things have these collimated relativistic outflows called jets, and the very high energy gamma ray emission is created in these jets. And the ones that we study in particular are blazars where these jets are pointed along the line of sight towards Earth. And this phenomenon that you get creates these spectral energy distributions where this is power and this is energy that have two humps. This hump right here is basically synchrotron radiation, and this hump right here has a variety of processes which can generate either leptonic or hadronic processes. But what we're looking at largely in our band are something called high-peaked blazars, which are low power but peak at higher energies. And this is the TeV band right here. And so we get just very small subset of these objects. We do sometimes get quasars and lower peaked objects, but generally when they flare and this distribution shifts outwards or upwards into an area where we can detect them. And so going into this thing that I've just alluded to, that these things shift, these blazars that we know are characterized by extreme variability, and this is a plot that I was very blessed to make about 11 years ago now, Parks 2155. And you can see this extreme variability right here. This is the brightest DC source in the TeV sky of a Crab Nebula. This is not the baseline state of this object, which is about a factor of 7 lower than this. And in one night, it popped up and it went up to 15 times the brightest source of the Crab, or about 100 times its DC flux. And you can see these these well-structured burst-like behaviors with rise times of order 60 seconds. Now, this is a galaxy, right? I mean, this is not a star or something like that. This is a very big object. And you're getting these, incredible rise times of 60 seconds, and flux, going up by and down by a factor of 100. And to basically do this, you need gamma ray burst-like Doppler factors of nearly 1,000 to pull this off. And so this is what keeps me going, what gets me interested to try to catch more of these events. So the VERITAS AGN catalog, there's lots of them. We get 3 of them in a single field of view, and there's so many of them now that we've decided to make constellations of them in our spare time. And we get about 600 hours of AGN data in a given year. It's about 50% of our overall program. 90% of the time is spent on blazars, where we're looking down a line of sight, and 10% of the time is when we're looking at them off axis, and you can see the lovely jet structure. And now we spend about 70% of the time looking at known sources and 30% trying to increase our catalog. And about a quarter of this overall time is spent chasing flares. We get about 3 to 5 major flares a year, these things that I really love. Okay. And one of these flares was OJ287. So we have this comprehensive discovery program where we basically look at all of the hardest MEV, GeV, AGN. Right now we focus on that 2FHL greater than 50 GeV catalog. We look at all of the brightest X-ray, bright, IBLs and HBLs, these high-peaked objects I showed you earlier, and we look at TOOs from a variety of sources. And one of these objects, OJ287, it's at a redshift about 0.3, and it's famous for exhibiting this sort of quasi-periodic behavior with a 12-year period going back about 100 years or so. And you can see this X-ray light curve up top. This is about 2 years worth of X-ray data from the Swift satellite, and you can see normally it's at around 0.1 counts per second. And it's kind of humming along, just being sort of boring. It's going to peak again in 2019, and then starting last fall, it started to get really bright. So about 5 times brighter in August, going along. And then it became visible to VERITAS, so we decided to take a look. We didn't see anything. We took a look a month later, didn't see anything. And then late January, we looked again during cloudy weather, and we said, hey, we've got something. It wasn't only about 4 sigma, not something you'd write a paper on. But we called up my friend at Swift and said, hey, we're seeing something interesting. We're going to hit it pretty hard the next couple nights. Will you mind taking a look? And they're like, sure, we'll intensify for you. Just keep it quiet because we don't want our competitors to scoop us. And so they looked, and they got the brightest X-ray point they ever found, and we correspondingly discovered it on the same night. And so this is how we all work together, and we get this bright thing. We had looked at it before, hadn't seen anything, and so what I've got here is a distribution of energy versus power. And what you can see here is the X-ray flux during this period, I've just shown 2 of them, just kind of goes up and down. It just gets brighter and bright and lower in X-ray. But what you see here is the archival Fermi data. This is what it's like on average. And what Fermi did is it didn't actually go up and down in Fermi. It slid left to right, which is just very, very odd. And we have to figure out how to model this. And if you guys are AGN experts, I'd love your help. So that's how we identify new TeV blazars. And so what do we do with them afterwards? Well, the idea is that we're going to use VERITAS and we're going to sample every known northern TeV blazar at least once a week when they're best visible. And if we catch a flare, we're going to intensify at all wavelengths. And so what this does is, this is a histogram of a number of blazars and our exposure over time. And as you can see, it peaks at low exposures. And over time, even if you look at it for just 15 minutes a week, over time, you build up this larger and larger exposure. And what I've also got going are optical exposures. We've got Fermi exposures. I get Swift exposures. I get everything. So I can build up long-term baselines and multi-wavelength spectral energy distributions over time for the entire catalog over a decade. So I'm looking for flares. If I catch a flare, I do something with it. And if not, at least I've got a big exposure with a lot of data that I can model over time. And so does this work? And the answer is yes. So this is a picture of a flare from NGC 1275. It's a central radio galaxy in the Perseus cluster. And we had looked at this for about 65 hours prior to last fall, and we had a very, very weak detection, less than 1% crab. I can give it to you in CGS units, but this, the crab is the brightest object. And we caught a flare of it in 2013 at 1% crab. This actually has two TeV sources in the field of view, IC 310, which is a head-tail radio galaxy, and NGC 1275. And so we looked at it for a half hour one night, didn't see anything. 3 nights later, we come back. We're looking at IC 310. We don't see anything, but we look at the field of view, and you say, hey, wait, it's bright in that field of view. So the next night we come back, and we hit it hard, and we see 5 hours of data. We get the brightest detection ever recorded, 15% crab. So it's 15 times brighter than it's ever seen. It goes away the next day. Well, I'd tell you more about this, but what happened in January of the next year, or January 1st of next year, is we get an alert from Fermi that says, hey, this thing's going crazy. We look at it, and suddenly it's 65 times brighter than it's ever been. And if you look at the plot here, all I can tell you just quickly is that this thing, the spectrum hardened, it's got a spectrum now of 2.8 as opposed to 4.1. And the prior flare, so this is not just a little bit harder, this is a lot harder. This is a photon index. This is, e to the minus gamma, so this is a lot harder. And unfortunately, though, if you look at the light curve here on that given night, you don't see any of those correlated or burst-like variations. It's just flat. So you get this big spike, it goes away the next day, something happened, and there's these spine sheath models out there and things like that, which has a major implication for it. Another flare that we caught last year, just doing these 15-minute exposures, this works really well, is in BL LAC. So we caught a flare in 2011 with these 15-minute exposures just before sunset. It was coming down. It was about 125% crab. So again, crab is the brightest DC source in the sky. We got about a 45-minute exposure, and we caught it coming down on about a 13-minute time scale going out. And when we caught it going down, about a week later, this new knot was caught in the VLBA images coming out. So we had this flare, and a few weeks later, a new knot comes formed, and you sort of tie in, okay, maybe these TeV gamma ray outbursts are correlated with the birth of new knots in AGNs. And so, well, that was good and fine, and moving fast, okay. And so later this year, in October, we had another flare, but this time it was much more correlated. In about 3 hours of data, you can see this right here, it rose up to about a peak of 180% crab and down again. And why this is unusual is that normally you get a sharp rise in a flat decay, a flatter decay, and you'd almost expect this curve to be inverted. And then again, we got another knot that's born during these superluminal images. Okay, so I'm running short of time, so I just want to go to this and then to my conclusions. So I went back and mentioned that we're building up these long baseline exposures in TeV and X-ray and optical. And so what can you do with this? And well, this is the spectral energy distribution of an average blazar that we would detect. It's one of my favorites, so it's not quite average, but it's not particularly strong. In 50 hours, we have a 12 standard deviation detection. It's only 2% crab. And so what you can do is you can make this thing, and modeling in the past has historically been plagued by degeneracies. Oh, it doesn't, you make this model, but you can tweak this parameter and it still works, and you're right. But the data now are so good that the black area shows the best fit model, but the gray area shows the range of allowed synchrotron self-Compton models. So you can fully constrain the spectral energy distribution now. The parameters you get out of this, and this is actually a 2D sort of mapping, if you will, of the range of allowed parameters in a couple of the spaces. The parameters now are constrained to a factor of 2 in basically all spaces, which is pretty terrible if you're trying to put something in orbit or build a bridge, but in astrophysics, a factor of 2 is amazing. And so that's what we're trying to do with the entire VHE catalog with VERITAS. I'm going to skip this and just go to my conclusions and say that VERITAS is running very well. We're funded to operate through at least 2019. We have about 60 sources, a lot of significant results with about 50 AGN papers in the pipeline. We're monitoring all the northern AGN to identify flares and to quickly follow up. These are our most recent flares. We're releasing major data samples for public use, and I just want to quickly show that picture again. This light curve is a huge flare of Markarian 421 in 2013. We just decided to release the data to the public for all to use. and we're always looking to collaborate. We are running ever short of scientists, in particular theorists. And so if you've heard about our results and you've read about our results, wonder if we have a favorite AGN that we've looked at, please come and talk to me. I'd really appreciate your help, and thank you.
One can make analogies with the gamma ray burst because in both cases you're looking down the jet, and the only thing you need to do is scale down the mass of the black hole from the AGN to the stellar mass scale by a factor of 10 million, and you get the right time scales, and perhaps some of the physics is similar.
Yes.
So that would be very interesting. But my question to you was, OJ287 that you mentioned, isn't that considered to be a binary black hole system?
There is a binary black hole system. There's also some helical jet models in there. I prefer the binary black hole because it does predict a lot of these optical outbursts well. So it's coming around again if you take this model in 2019, and so we're on the cusp of it going up. The last time we looked was on the back side of it.
I just want to follow up on this binary black hole. Is it a preference, or is there any substantiation for it?
It has, I'm reticent to say preference, but it has predicted a number of previous behaviors well.
It's a reasonable model.
It is a very reasonable model.
But then the question is, why isn't the jet processing? Why do we see it all the time?
Yeah.
Well, I guess it depends on the orbital period. Yes. Okay. Other questions? Well, if not, everyone is invited to come to the CFA colloquium where we hear more about VERITAS. Thank you.
3 years.
This side.
Okay, can you hear me? Yeah. Good afternoon, ladies and gentlemen. It's actually a pleasure for me to talk here. And today I'm going to talk about a project that has been done when I was visiting Johns Hopkins University back in 2 years ago in collaboration with Professor Kamyankowski and Emma Dumashoni and Jens Yubka. So it's actually about probing the scale dependence of non-Gaussianity through the CMB Spectral Distortion. Let me just start with a very quick introduction and outline of what I'm going to talk about it today. So first of all, I would start with a very brief definition and motivation for the spectral distortion, as well as the creation of these, signals. And afterward, we actually talk about how we can use this spectral distortion as a very unique way to shed light about the scale dependence of non-Gaussianity. It's actually air universe cosmology. And afterward, I would like to trying to search for some particular primordial realizations that can actually lead to some detectable, large enough and big enough, detectable signals for the spectral distortion. So let's just start with a very quick and first look at the CMB spectral distortion. As we all know, one of the great predictions of the standard model of cosmology is the cosmic microwave background. And it was actually observed first by the Kobe Frost, and then it was so important that it's to a Nobel Prize in 2006. If you look at the spectrum of the intensity map that they actually observed, you actually see that there are 3 different parameters right here. So one of them is actually the mean temperature, which means that to a very, very good degree of accuracy, you'll end up with a black body spectrum. However, you may also have some distortions or deviation from the pure black body spectrum, which actually can be determined by these two distortion parameters. That is the main purpose of this talk today, and we call it either the chemical potential mu or the Y Compton potential. And these are actually, there are some bonds on them which are they must be actually less than 10 to minus 5. So these are actually, these are three parameters that has been specified by the Kobe-Frost and, maybe, Prism and Pixie. They can actually shed more light about them, by 3 orders of magnitude. And as it turns out, they are very, very informative in such a way that any physical process that during the cosmic history of the universe can actually inject energy into the plasma could lead to, if you go further in the redshift, as I will mention in a minute, they actually lead to these 2 parameters. So they could be very informative piece of information for us, and in addition, they could actually be a good measurement for the universe cosmology. And even more importantly, they are complementary and co-independent of the piece of information that you can actually get, from the CMB itself or from the larger scale structure. So it's worth to take a look at them in more detail. Now let's go a little bit further and see how they can be created. So if, as we may know, before the redshift of 2 million, any injection energy inside the thermoplasma could be very quickly thermalized in such a way that double Compton scattering and Bremner are so efficient that any injected energy would lead to a lot of free photons, and they can actually thermalize further and further using the Compton scattering, and you end up with just changing the temperature. However, after of this redshift of 2 million, if you inject any energy by any mechanism that are just quite a lot of them, as you can see, because of the messy, complex, things that can actually in the, in the thermoplasma that we're looking at, it ends up with actually some distortion that depends on the redshift and also the scale. You could actually, end up either with the mu distortion or with the Y distortion. So in this cartoon, we can actually see that when you look at the redshift or the thermal history of the universe, you really see that this is actually the area for the CMB spectral distortion. So these are very important. There are so many different ways to create them up, and therefore this is super important to actually be able to talk about any mechanism that could actually uniquely determine them. So instead of talking about any different mechanism that can create them up, with collaborators and we just try to shed light, how we can talk about the origin of this. And it turns out that there is a very nice way of doing that, and it can actually be done through the cross-correlation of that distortion parameters that I just mentioned with the temperature fluctuations. So if this cross-correlation is non-zero, you can actually say that it could actually come from the universe. And for those of us who are more interested about the inflationary universe, it can be a good probe of inflation, and even more, it can be a good probe of FNL. So we all know that Planck was not successful enough to detect non-Gaussianity. However, as I will mention in a moment, this kind of cross-correlation can actually go to a window which is completely outside the window of the CMB and also the larger scale structure. So these are very important, way to actually shed light about the origin of them, and furthermore about the primordial universe. Now let's have a very quick look at this, and just very, very simply, as simple as possible, see how it can actually go. Instead of going to a Fourier space and the complexity of doing that, I just lead to the real space. So that, and I actually talk about the fractional change in the chemical potential due to any change that is actually due to the primordial non-Gaussianity. So you could very easily show that the fractional change in the chemical potential is actually proportional to the FNL. And therefore, this, if you can actually measure it, you can just shed light about the FNL. So on the other hand, you can also talk about the fluctuation and, the fractional change in the temperature fluctuation, and you can further cross-correlate them up, like what I said before, and therefore you can actually see that this cross-correlation will be proportional to FNL. and also for this guy. So at the end of the day, you end up with these two parameters, which are the cross correlation of either chemical potential mu or chemical potential y, and Compton potential y, and then you can actually go one further step and calculate the signal to noise ratio for these two guys. Now we want to have one sigma detection for this kind of signal, and you can actually see that the FNA required to have this kind of, one sigma level of accuracy is quite a lot actually. It's 220. So we know from the Planck that this is not going to be the case. Actually, the local non-Gaussianity is going to be 1/10 of that actually, or even 100 of that. So what is wrong with that? I just wanted to show you this very simple way to tell you that, okay, then we can actually shed light more about this, and we can see that in order to detect the spectral, and FNA through the spectral distortion, you really have to have a scale-dependent non-Gaussianity, which just means that during the CMB scale, which is roughly k of order 10 to minus 2 and so, you can actually have a very tiny consistent with the Planck data. And when you go to further and further scale, remember that, for example, for this spectral distortion, it was more than 1 megaparsec inverse, and it can actually easily go to 10 to the 4th megaparsec inverse if you actually consider the Compton, y and mu distortion. So in this case, we can actually see that if we have a scale-dependent non-Gaussianity, this is going to be a unique way of shedding light about that. And furthermore, so this was the first thing that we figure out, and afterward we end up with a very, very tough work of finding some inflationary model which are consistent in such a way that they are consistent with the CMB result, like a Planck result of having little tiny FNR during the CMB scale, and then goes up when you actually consider this K of order, for example, this guy is actually some inflationary model. That's what we mentioned if I have time. But you can actually see that in some particular inflationary model, that's now I just have some figures of them. You can really see that is FNL is just very tiny, and then you can easily go to 2000 or 200, and it's just very, very easily going to be possible. So I'm going to, in the remaining few minutes, I'm going to actually tell you a little bit about this kind of models. So the first class of example is actually going to be happen if you have a heavy field. So you know that if you have a heavy field, in addition to the inflation, because of the oscillatory features of that, heavy fields, there could be some resonant features in the spectrum, and around that resonant features, you can actually end up with the big enough values of the FNL. So this is a good help, because you can actually see that this resonance, I can actually manage it to happen on very small scale, which are consistent with the CMB, distortion scale, and still within the CMB scale, which are 2 or 3 orders of magnitude higher and larger scale as compared with the distortion, still on end up with little tiny FNL. So that was one class of examples that we consider, and another class of example can actually happen in gauge hybrid inflation. I apologize that I cannot really show you the model because of the lack of the time. However, you can actually do the calculation, and you can see that again for K. Thank you. I'm very close to the end of the talk. So you can actually see that within the CMB scale, you can end up with the very tiny values of the FNL. But then when you go to higher and higher values of the K, which is good enough for the mu distortion that can actually goes to 10 to the 4 megaparsec inverse, you can actually end up with 200 or 300, which is what we really, really needed. So then, these two examples of the models are actually consistent with the Planck and also distortion, and our expectation for the 1 sigma level of accuracy for the distortion. So this brings me to the conclusion of talk. So actually, in this short presentation, I wanted to tell you that although there are so many different ways to create a CMB spectral distortion, it's still good and novel and worth to actually think about a unique way to shed light about them. I mean, not just considering another kind of of, model that can create them up, but just consider how we can, in principle, distinguish them up from the rest of, rest of the signals and rest of the phenomenology that actually can lead to this CMB spectral distortion. So we did some quick estimation, and we figured out that there are indeed some inflationary models that are both consistent with the CMB in such a way that the FNL is actually quite small for them within the CMB window, which is consistent with the Planck satellites, and of course they are also consistent with the expectation for having good enough and large enough values of the spectral distortion. So this brings me to the end of this talk. Thank you so much for your attention and for invitation.
Razieh, your limit or constraint on FNL that you mentioned, it seemed to depend on the average value of mu divided by the minimum value in your expressions.
Great.
Or the average value
Let's
of
go back. Right. So it's actually a great question. So this is true, and in fact, this is actually, these parameters, we just consider the average mu. If you really consider the, prism and pixie, it could actually go to 10 to minus 8, and so. So these are going to be, when we consider these two, we just consider them to be of order of 1, and then we end up with the amplitude. So the amplitude should be of order of 200, right? But the rest of them, they are just, dimensionless parameter which are order unity. And, we just parameterize it in this way so that we can just directly read off the value of the amplitude, right?
But the strange thing is if mu is bigger, then you can go to smaller FNL. If the average value of mu is bigger.
Yeah.
So in fact, a signal that is easier to detect.
Absolutely, and we can imagine, right?
Would bring you to an easier path to constraining FNL. If you have a larger average value of mu, then you would be able to probe smaller FNL.
Actually, there are also mu mean in there, so
right.
there could be some cancellation between these two. Okay. It's kind of, they are both coming from the same source, right? It's actually, right.
Okay. Any question over there? There was a question.
Which
Sure.
scales are this spectral index most sensitive to?
Okay, very nice. So actually, let's go back to the scale of importance. So we know that if we actually have some signals, they could happen some seek damping and due to this kind of collision and so forth. So you can actually see that this scale, in order to have the Boyd distortion, the K should be from 1 to 50 megaparsec inverse, and for mu scale is actually from 50 to 10 to the 4th megaparsec inverse. So they are very, very, very small scale, and that's the advantage of considering the distortion, because they are all completely outside the window of larger scale structure, Lyman alpha, and any other guys, right? It's just very a small scale.
Okay, we need to take a group photo, so let's thank Razieh again.
Thank you.